Alright, hello everyone, and welcome to my channel. This is an educational channel, and we look at a lot of different theories of everything, all-encompassing theories, magnum opuses from obscure authors, ancient and modern, different paradigm shifters, or anything else that could really benefit you if you studied it, but you haven't, probably because you haven't heard of it, and things that have been suppressed, holistic theories, all kinds of stuff. But we like to go deep in these topics and give you a thorough presentation. And today is our 405th video that we've done on the reciprocal system of theory from Dewey B. Larson. And the idea behind the reciprocal system of theory is that we live in a universe of motion. In Larson's universe of motion, the universe is literally made out of motion. It's not made out of matter. It's not made out of energy or force or anything else. It's made out of motion. And specifically, it's made out of a kind of motion that he calls scalar motion. Scalar motion is a motion of a more generalized, non-localized type. It's a motion that has a magnitude, but it has no specific direction. And so you would be able to model this kind of motion with a balloon with dots on it. If you take a balloon with dots on it and you blow up the balloon, all of the dots will be moving away from each other. Every dot will be moving away from every other dot. And but they will not be moving in any specific direction. Just either away from, if you're blowing the balloon up, or toward each other if you're sucking in the balloon. But there is no specific direction. Each dot is moving away from each other dot. In fact, each space between the dots are also moving away from each other space. So it's the outward motion of the balloon itself that you're keeping track of. And that motion will not have a specific direction unless you arbitrarily assign a reference point. If you arbitrarily say, this particular dot, we will consider this dot to be motionless. And then when you do that, you will be able to, discern different directions between one dot and another dot. But that is not reality. That is basically stopping the universe, stopping a moving universe and taking a snapshot. So now Larson had these first inklings way back in about 1930, but he kept his day job and plugged away on this kind of a project at night, and took him about 25 years to arrive at his fundamental almost 30 years to arrive at his fundamental postulates, two fundamental postulates, around 1959. The first postulate states that the universe is composed of the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. That's why we call it the reciprocal system. Two reciprocal aspects, space and of motion, space and time. So the universe is made out of motion, a scalar motion, and that motion is the relationship between space and time. And that sets up a generalized reciprocal relationship between space and time. Motion is basically a fraction, with space or time as the numerator and time or space as the denominator. All forms of motion fit this description, and this is including matter, energy, and force. Things that we originally thought that the universe was made out of turn out to be just different kinds of motion. All of our scientific quantities are simply time over space or space over time, with time or space coming in multiple dimensions, potentially. So in Larson's system, speed is space over time. The bicycle is moving 10 miles per hour, 10 miles of space and 1 hour of time, space over time. Acceleration, the rock fell at 9.8 meters per second squared, 9.8 meters of space, 1 second per second of time, space over time squared. For Larson, energy was time over space. It took me 3 hours to move that thing 1/2 mile. 3 hours of time and 1/2 mile of space. For Larson, matter was time to the third power over space to the third power. Pressure is time over space to the fourth power. Magnetic flux times to the second power over space to the second power. And so on and so forth. So just like all other reciprocals, space or time have the identical qualities, one of which is its coordinate nature. And this, again, is kind of stopping the universe to see that space is still. There's a still frame of space, and it is three-dimensional. X, Y, Z coordinates, or at least you would say multi-dimensional. Larson says three-dimensional X, Y, Z coordinates in a still frame or volume. And since Larson observed this about space, he also imputed this about time, because space and time are reciprocals, so therefore they are identical. So space, except that they are in different order. So space has 3 dimensions, as so does time. He calls this coordinate space and coordinate time. And then clock space and clock time are that scalar viewpoint. Okay, space is always getting farther and farther and farther apart, just like on the surface of an expanding balloon. And that is what we perceive about time as well. Time is always getting later and later and later and later. So Larson refers to that as clock time and clock space. Space and time also come only in discrete units. You have to have a full unit of space and a full unit of time. They are quantized. There is no half units or a fraction of a unit. There's only full units. And if you have exactly 1 unit of space in 1 unit of time, you have what Larson calls unit speed. 1 over 1 equals 1. And that unit speed is equal to the speed of light. So the speed of light is 1 in this universe, Larson's universe. And that means that the speed of light is the background speed of the universe. If you have a universe that's made out of nothing, that has no features, it has nothing in it, you still have motion outward at the speed of light in all directions. This is the default speed. This is the empty universe. This is the origin, the ether, the null speed, the neutral point, the reference point. Larson refers to it as the progression of the natural reference system. And so Larson makes his measurements from that point, whereas legacy science makes its measurements from 0. Larson measures from the speed of light outward in all directions. And therefore, half of Larson's universe of motion is moving faster than the speed of light. Whereas in the legacy science, the universe is, the speed limit of the universe is the speed of light. Nothing moves faster than the speed of light. So that is only covering half of Larson's universe. In Larson's universe, half the universe is moving slower than the speed of light, but half is moving faster. He refers to those two sectors as the material sector and the cosmic sector, respectively. So this cosmic sector is something that legacy science doesn't know anything about. But they could catch up quickly because the dynamics of the cosmic sector are identical to those of the material sector, except that they are in reverse order, or the roles of space and time are reversed because they are reciprocals of each other. So in the material sector, you have relationships based on clock time. Time is always getting later and later and later. And coordinate space. Space is three-dimensional in a still frame. And in the cosmic sector, if you cross that speed of light boundary and you move to the faster than the speed of light sector, then you have coordinate time, 3 dimensions of time in a still frame, and clock space. Space is always getting farther and farther and farther apart. So, now another difference is that in the classical interpretations in legacy science, space and time are seen as being the container of the universe. The actors on the stage act out their dramas on a stage made out of space and time. They go about their paces in space and in time. But in Larson's universe, space and time are not the container of the universe. They are the contents of the universe. So space and time are the contents of the universe. The universe is made out of space and time, not existing in space and time. The actors on the stage are made out of space and time. Okay, now today we are on our second installment of going through Larson's 1987 book called Basic Properties of Matter. Now this book is basically, Larson took his two fundamental postulates and then through a process of deduction, if this then that, so he goes through a detailed process of deduction, which I detailed in the 15 videos that I did about a year ago called The Outline of the Deductive Development of the Reciprocal System. He arrives at a theoretical universe. What would my universe look like if my postulates were true? And I believe I haven't given you the second postulate, but it's not that important. But it is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So the second postulate is just really about math and geometry, and it's under dispute as well, but by many of his own followers. The first postulate is where most of the action takes place. But so he took those two postulates, and then eventually through a process of deduction, he arrived at a theoretical universe. And then in his books, especially in this book, Basic Properties of Matter, he compares his theoretical universe, the universe he came up with in his head, using two simple rules that are laid out in the postulates. And he compares that with the so-called actual universe that has been measured through experiments in laboratories by the legacy scientists. They compiled their data in various scientific tables, atomic tables, where they have the whole periodic table there, and they show the various basic properties of matter, of the various elements and compounds. Take the first element, hydrogen. What is the melting point of hydrogen? What is the boiling point of hydrogen? What, is the specific heat? What is the compressibility? All of these different qualities of hydrogen have been measured by the legacy scientists, and they have also been determined theoretically by Larson. How similar are those two measurements? One theoretical, and one is empirical. So that's what this book is about, Basic Properties of Matter. We just covered the preface last time. So today we're going to start out on chapter 1, which is called Solid Cohesion. So this is going to be covering the elements in their solid state. And in their solid state, they tend to stick together. And so Larson is going to end up coming up with a theoretical expression or an equation for the solid cohesion that he determines from a process of deduction. Okay, we'll start it right here. The consequences of the reversal of direction in the context of a fixed reference system that takes place at unit distance, okay, that's again 1 unit of space, unit distance, and 1 unit of space is approximately 4.56 times 10 to the minus 8 meters. 1 unit of time is approximately 1.52 times 10 to the minus 16 seconds. Okay, so the reversal of direction in the context of a fixed reference system that takes place at unit distance were explained in a general way in chapter 8 of chapter 6 of volume 1. Chapter 8 of volume 1. Volume 1 was nothing but motion. We went over that about 6 months ago. That's his book on atomic physics. So basically, the general idea is that the universe is quantized. So when you have less than 1 unit of space, you do not have space. You only have time. And when you have less than 1 unit of time, you do not have time. You only have space. You have the inverse quantity. And so when you're dealing with atomic size, you are less than 1 unit of space. And so you're in what Larson calls the time region. The time region is the region within 1 unit of space. And the space region is the region within 1 unit of time. Larson explains all this in his book, Nothing But Motion. But here he just refers to it, chapter 8 of volume 1, and already after one sentence of his book, he has lost the majority of his readers because they don't know what he's talking about and they haven't read the first volume of his book. So that's kind of what I'm talking about, where I say that Larson, I'm sorry about that. Let me take care of this. We all have our weaknesses of a presentation. I have an alarm clock that I don't know how to turn off. And it goes off at the same time every night. But anyway, sorry about that. So that's why I say Larson is a good writer, but he's a bad teacher. And so a lot of times Larson just refers offhandedly to scientific concepts that the layperson doesn't understand. Larson is writing for a scientifically educated audience. He's writing for other chemists and other physicists. And unfortunately, that's unfortunate, because I think that Larson's best audience would actually be the layperson, the intelligent layperson or child who hasn't taken any science classes yet. You know, a 13-year-old who hasn't started high school yet, so they haven't really taken any chemistry classes yet. They haven't been indoctrinated into the standard paradigms. Once indoctrinated, it's harder to grasp Larson's system, because you have to forget stuff. You have to unlearn stuff before you can really learn Larson's paradigm. And so I think he made a strategic error in targeting his books toward the scientific audience. And here, you know, he's already kind of excluded a good portion of his audience by just saying, the reversal of direction that takes place at unit distance was explained in a general way in chapter 8 of volume 1. You know, a normal reader can just read that and then just move on and just kind of slough it off, but they've already kind of lost. So basically the idea is that when you cross that unit distance boundary, the rules change. You are no longer in a realm of space. You're in a realm of time. And so you have to take that into account when you're dealing with the solid of the solid cohesion. A question about solid cohesion. The solid is, by definition, by Larson's definition, is something that occurs within unit distance. A solid is when one or more than one different atoms or molecules are within 1 unit of space of one another. They do not interact in space, they interact in time. And so the reversal of direction occurs, and the equation that you would need to use is different. It's the reciprocal, more or less. Okay, as brought out there, the most significant of these consequences is that establishment of an equilibrium between gravitation and the progression of the natural reference system becomes possible. Okay, he's already lost you because he hasn't really explained what gravitation is and what the progression of the natural reference system is. The progression of the natural reference system, as I mentioned, is the fact that space and time are moving outward in all directions at the speed of light. And gravitation is the reverse of that. Gravitation is basically when you take that expanding balloon with dots on it and you turn it into a contracting balloon with dots on it. When you suck in the balloon, all of the dots are moving toward each other. And that is analogous to gravitation. Gravitation is not a force like a force field that you would normally think of, where there's action at a distance, where one dot is attracting another dot. That's not what gravitation is in Larson's system. That's what the legacy scientists would call a force field. Between one dot and another, there's a force, an action at a distance going on between two dots. In Larson's system, all dots are moving toward each other. So there is no force. It's just the natural movement of a contracting balloon, of the surface of a contracting balloon. And so he says here that, as brought out there, the most significant of these consequences is that establishment of an equilibrium between gravitation and the progression. So there's something in between those that establishes a solid cohesion. The progression of the natural reference system is moving the particles away from each other. And the gravitation is moving the particles toward each other. But here we have a situation where the particles are not moving relative to one another. They are staying in the same general, approximate distance between each other. And so that is the equilibrium between gravitation and the progression. There is a location outside unit distance where the magnitudes of these two motions are equal. The distance that we are calling the gravitational limit. But this point of equality is not a point of equilibrium. Okay, so he's distinguishing between the equality and the equilibrium. This is outside unit distance. Okay, so this is when the particles are farther apart than the speed of light, or than unit distance. And there is a situation where the gravitational so-called force and the progression of the natural reference system are equal, but that is outside of the unit of distance. He calls that the gravitational limit. A thing that you might that might shed some light on this is that in addition to your surface of an expanding balloon where all of the dots are moving away from each other, that has also been observed through the Hubble telescope, or not the Hubble telescope, but by Hubble through a telescope, that all of the distant galaxies are moving away from each other. So all of the galaxies are participating in a similar type of motion, even though they use that to come up with an excuse for the Big Bang. The Big Bang would only, that there was a center point of that explosion, and then all of the galaxies are kind of on the periphery of that explosion. But that is basically assuming a still reference point. And so if you're not ready to assume that our galaxy is at the center of the universe, which kind of Copernicus put on the scrap heap, then you also would be able to assume that our galaxy is also participating in that motion, which is more like the surface of a balloon. Okay, so all of the distant galaxies are moving away from each other. all of the galaxies are moving away from each other, but some of them are close enough together that they actually are moving toward each other. So there is a distance somewhere there between the two, where the two forces, or so-called forces, are equal. And Larson refers to that as the gravitational limit. On Earth, I believe the gravitational limit is like 3.5 light years. So if something is within, I'm sorry, not Earth, but the sun. So if something is within like 3.5 light years of the sun, it tends to move toward the sun. If it's more than 3.5 light years away, then it tends to move away from the sun. And then there is an extreme gravitational limit where the force of gravity is completely nullified, and the body moves outward at the speed of light, which is the speed of the progression of the natural reference system. So gravitation is completely nullified at this second gravitational limit, which is, I think, for the sun, it is something like, I think it's like 12,000 light years or something like that. Okay, so that's about as far as we're going to get. I think we read about 8 lines of Larson before we, that's why I'm trying to do this, because I've read this book like 10 times, and I've had to figure this out the hard way. And maybe this was obvious to you. If you're a scientist, maybe, I guess, or if you're a hell of a lot smarter than me, then I guess you could figure this out yourself. But I'm trying to kind of hold your hand through this and go through the process step by step. And so we'll just, start again tomorrow. And, basically, we talked about the gravitational limit. Eventually, we'll get around to talking about the point of equilibrium, which is the interatomic distance. Okay. Thanks for tuning in today, and have a